Good morning. Let us start the class of analog electronic circuits. In module 3, we have been discussing about the hybrid model, and we had already discussed the base bias or fixed bias circuit of BJT. And I had told you that the voltage divider bias is almost similar to the base bias, only the difference is that Zi is going to change to R1 parallel with R2 parallel with HIE. So today let us see one more circuit called unbiased emitter bias. In fact, this particular circuit was not discussed in our DC analysis because we were focusing more on amplifiers there. Still, in the book Boylestad, he discusses this particular circuitry for the sake of analytical interest. So, you can see the hybrid model of the transistor here. I'll just highlight this area. Now, this HIE with HFE and IB is the hybrid model of the BJT itself. And optionally, you can have one parallel resistance here where you can write it as 1 over HOE. You already know that I is input, O is output, F is forward, and R is reverse. That HRE we are not using anywhere here because the value of HRE will be quite negligible. And this E stands for emitter. So now the BJT is there here. There is this RB here. There is this RC here. And there is this RE here. So can you really visualize the actual circuit of BJT? Can anyone tell me, by looking at this particular hybrid equivalent model, can anyone tell me either orally or in the chat box what will be the circuit here? Circuit in the sense, you visualize the BJT. BJT's collector will have what, emitter will have what, base will have what. Can you visualize that circuit diagram and can you tell me either orally or in the chat box? Anybody is willing? Okay. If it was offline class, I would have forced one of you to come to the board and write this circuit at least to make an effort. Because unless you make an effort, you will not be able to understand. Anyway, I only will write it here below. Let me try to write it. So you will have transistor and then you will have RC and you will have RB and you will have VCC. Okay, you will have plus VCC. So here you will have output, here you will have input. This is VI. I am not writing the capacitance here. This is V0. So you can see correspondingly from base to VCC, let us say I write it as VCC. From base to VCC, there is this RB. And from collector to VCC, there is this RC. Anyhow, RC one end is AC ground, RB one end is AC ground. So this is that ground. This is that AC ground as such. Now, this is that particular transistors model at the input HIE and at the output HFE IB. And we have taken Vi and V0. What about the emitter now? In the earlier case, we always used to connect the emitter to ground. But now this is told that this is unbypassed emitter bias. Means in this particular circuitry, the bypass capacitor is not used. The bypass capacitor is not used because of some other analytical reasons. In fact, we have to connect a bypass capacitor there. That is because of the stability of the Q point. If at all AC signal comes at the emitter, that will affect the stability of the Q point. In the sense, if there is the variation across that RE, the voltage across RE is going to vary when the input signal AC is also coming there. It will affect our Q point. Just to have that stability, one capacitor is connected from the emitter to ground directly bypassing the RE. We had discussed this at length before. But here in the circuit now, it is taken as unbypassed RE. That means there is this RE. This is that RE. So across RE, there is no bypass capacitor as such. That is the idea here. Let us not really worry more about why there was no bypass capacitor. Okay, because later on I am going to discuss about low frequency and high frequency analysis, where we are going to discuss about which capacitor is dominant in the whole circuitry in deciding upon the bandwidth or the frequency response. So here, if bypass capacitor is not used, the circuit will have an advantage. The advantage in the sense, the frequency response may be having an improvement or the bandwidth may be increasing. That is the idea. So this is that unbypassed emitter bias, where there is RE from the emitter till ground. There is no bypass capacitor there. Let me stop annotating and let me continue now. Now let us proceed with the hybrid modeling of this particular circuitry. You can see that as emitter is not grounded, as this physical RE is there from emitter to ground, the analysis here can be slightly complicated. In the sense, if you have to calculate Zi now, we know that there is RB and RB in parallel with this network, this whole network. Similarly, Z0 is also RC parallel with this whole network. In the earlier case, we could have easily written, if there was a bypass capacitor, then we could have easily written that Zi is RB parallel with HIE. And we would have written Z0 as RC parallel with 1 over HOE. That 1 over HOE is not shown here. You will have to visualize that. But because of this additional RE, there is a slight complication here. So let us see now how to compute the input impedance and output impedance and voltage gain for this particular network. We can write the expression now, Vi equals HIE into IB plus IB plus HFE into IB into RE. Just look at this. There is this total Vi from the base till the ground. So I can write an expression for Vi as HIE into IB. Now current flowing through this RE is IB plus HFE into IB, because IE is what? 1 plus beta into IB. So you can see here, current through RE is IB plus HFE into IB, that into RE. So I can write an expression for the input voltage in this manner. So now this is HIE into IB plus IB into 1 plus HFE into RE. Now let us find out ZB, that ZB is the input impedance at the base. Later on we can write Zi as RB parallel with ZB. I hope you get it. Input impedance is RB parallel with this whole network at the base. Let us call this as ZB, impedance at the base. Then impedance at the base in parallel with RB is going to be Zi. So now ZB is Vi by IB. Impedance at the base is input voltage at the base divided by base current. So this IB gets cancelled and we get HIE plus 1 plus HFE into RE. We can ignore that 1. When we ignore that 1, it is HIE plus HFE into RE. This is ZB. Now ZI is RB parallel with ZB. That's all. That means ZI is RB parallel with HIE plus HFE into RE. This is the expression for input impedance. Now let us try to find out the expression for output impedance. As RC is much lesser than 1 over HOE, Z0 is RC itself. Now, why did we ignore the effect of RE? Why did we ignore the effect of RE here? Should we not consider RC in parallel with this current source and RE? Can anyone tell me? Just like we considered the input impedance ZB here at the base and we computed ZB and we made it parallel with RB. Should we not find out the impedance here across this HFE, IB and RE, and should we not make it parallel to RC? Why are we directly writing Z0 equals RC if we assume that RC is much less than 1 over HOE? Otherwise, Z0 has to be RC in parallel with 1 over HOE. So my question is, why did we ignore this? Why did we ignore this network when we are computing Z0? Is it not that it is RC in parallel with, we should find out this ZC, just like we found out ZB, should we not find out ZC here, considering this HFE, IB and RE? Any answer? RE is already connected for in-out impedance. Yeah, that is fine. We had considered RE for input impedance. Should we not consider RE for output impedance is my question. When this RC is in parallel with the whole network, should we not consider RE here also? How can you write directly Z0 equals RC itself? That is my question. But its effect will not be considered as it is low. Now, if it is low, it has to be considered, right? When two resistors are in parallel, the effective resistance will be less than the least resistance there, right? So, if RE is considered as parallel with RC, if RE is lesser, effective resistance will be less than RE. So, we should consider. Why are we not considering? Any other answer? Okay, I'll tell the answer. The answer is RE is not a standalone resistor here. RE is in series with the current source. Any current source will have a very high resistance. In general, any current source there will have like this, HF into IV. So, when we consider this current source here, we will not take an effect of RE there. So, we can directly write RC as output impedance, because we are measuring the output impedance at the collector terminal and we can fully ignore the effect of this current source. That way, we can ignore the effect. Fine, let me proceed now. Now, as RC is, this I have already told. Now, let us find an expression for voltage gain. V0 is minus HF into IB into RC at the output. It is nothing but the current into resistance. So, minus HF into VI by ZB, because IB is nothing but VI by ZB into RC. Therefore, voltage gain is V0 by VI, that is minus HFE into RC divided by ZB. So, we already have an expression for this ZB. We can write AV equals minus HFE into RC divided by HIE plus HFE into RE. So this is where we have completed the hybrid analysis of unbypassed emitter resistors circuitry. Let us go to the next one, that is emitter follower. I hope you can visualize the circuit diagram for the emitter follower, or else to help you visualize, let me write the circuit diagram here. This is the circuit. Now this will be plus VCC, and you will have input here, but output you will take here. Output you will take at the emitter. This is now Vi. I am very crudely writing because I am trying to write using the mouse itself. You will have to bear with this. Anyway, let me admit the student who is waiting. Fine, now you can see from the base to the collector there is this RB, that is this particular RB, and collector is directly connected to VCC. So you can see this collector is directly connected to ground. Collector is directly connected to ground because VCC is AC ground. Now at the emitter we are taking output. We had seen the circuit earlier in the first module, where we had derived the voltage gain of this circuit as unity. That is why whatever is the input voltage at the base, it is available at the emitter. That is what is called as emitter follower. Emitter is following the input. There is no voltage gain, but there is only current gain. So this is that circuit, and you have RB, you have RE here. So you can see this RE connected to ground. And then we have HIC. Why it is HIC? Because it is a common collector configuration. Emitter follower is basically common collector configuration. Input is at the base, output is at the emitter, collector is common to input and output. That's what is called that way. So you can see this RE also here. RE is connected to ground, emitter is not connected to ground, whereas collector is connected to ground. Now, why did we discuss the unbypassed circuit is to discuss the emitter follower. That was our idea. We discussed the earlier circuit called unbypassed emitter bias. There we already found out the input impedance for that unbypassed emitter bias. Now, that analysis is helping us in this emitter follower because input side is same. If you recall the earlier circuit, let me show you the earlier circuit. See, this was unbypassed emitter bias. Now the input circuit is same. Input circuit is same. Only thing is output is now taken at the emitter instead of the collector. Collector is connected to VCC, so we have AC ground here. That is the only difference. Otherwise, input analysis is same. That is where purposefully we discussed unbypassed emitter bias earlier. So Zi is same as that of the unbypassed emitter bias. So let us try to find out the other factors, output impedance and the voltage gain. Now IE is 1 plus HFC into IB. I cannot admit the students. We are in the waiting the lobby. That admit button is not appearing. Okay, let me continue the class. IE equals 1 plus HFC into IB. Why HFC? Because it is a common collector configuration. So that is 1 plus HFC into VI by ZB. Now for ZB, from the previous circuit, we have an expression which is HIC plus HFC into RE. So substituting 1 plus HFC into VI by HIC plus HFC into RE, we can ignore this 1 there. So IE equals HFC into VI by HIC plus HFC into RE. We can bring that numerator to the denominator. Okay. So, this HFC we will bring it down. VI divided by HIC plus HFC plus RE. We can write an expression for emitter current in this manner. Now we can write a network for this particular expression. You can see this network where you can see with respect to this particular expression. Just visualize this particular expression. There is this VI. There is this VI. And there is this HIC by HFC plus RE. HIC divided by HFC plus RE. That means, as far as this IE is concerned, HIC plus HFC and RE are in series. You can visualize this loop this way. When you visualize this loop, HIC plus HFC plus RE is there. So, HIC divided by, sorry, here I told plus, it is HIC by HFC. So, here it is HIC by HFC, we have one resistance and we have RE another resistance, and that is how current is flowing, IE is flowing, and VI is there at the input. Now, V0 we are taking only across RE. So, you can see this V0. We are taking output across RE, right? That means at the emitter we are taking the output. So, when you look from the output side, you will see that it is HIC by HFC and RE, they are in parallel. So, just by looking at this network, we can write an expression for Z0, that is HIC by HFC parallel with RE. What is the question there? In the numerator, shouldn't there be plus VI also? It is there. See, in the numerator, this VI is there, no? VI is there in the numerator. So, using this expression only, we are writing this network. You can see VI is there, then below there are two resistors in series. That is the expression given for current. So, this is the loop now. So, you will have to visualize IE in this manner. IE is VI, then series resistance, then one more series resistance, RE. But we are taking the output at the emitter. So, we have to write V0 here. I hope it is clear. 1 plus HFC into VI equals VI plus HFC into VI. Yeah, that one we have ignored, right? 1 plus HFC can be ignored because HFC is nothing but it is equivalent to beta, just like HFE. That is why that unity is ignored. Okay. So, output impedance Z0 is simply this HIC by HFC in parallel with RE. That is the expression for output impedance. So, let me continue. We had already an expression for Zi, that is same as the earlier circuit. Now, we have an expression for Z0. From this network, we can again write V0 equals VI into RE divided by HIC by HFC plus RE. You can look at this. This is nothing but a voltage divider network, two resistors. When there are two resistors here, now we can simply write V0 is across RE. So, total voltage across the voltage divider network is VI. VI divided by HIC by HFC plus RE into RE. So, now we will divide V0 by Vi. When we divide V0 by Vi, automatically Vi gets cancelled here, right? So, AV is V0 by Vi, Vi gets cancelled here. That is capital RE divided by HIC divided by HFC plus capital RE. Now, look at this. There is this HIC by HFC and there is this RE. If this HIC by HFC is much less than Re, then what will be the voltage gain? It will be equivalent to unity. Provided Re is much larger than HIC by HFC, then voltage gain can be Re by Re, that is equivalent to unity. So that is the idea. Otherwise, we can always find out HIC by HFC, we can find out the voltage gain. But anyhow, we know that in the case of emitter follower, voltage gain is almost equivalent to unity. Fine. Let us have an exercise now for this common collector circuit. Common collector circuit is nothing but emitter follower. You are seeing this circuit, that's an emitter follower. We are taking output of the emitter, and you can see there is an input source, then we have a series resistance Rs, then we have a DC blocking capacitance, then we have RB and RC, we have a AC coupling capacitance at the output, then we have a load 4.7 kilo ohms, and we have this RE 2.5 kilo ohms. The value of RB and RC are not explicitly stated here, but value of HIC is given 1 kilo ohms, HFC is given 50, HOC is given 20 microsiemens. Even if the value of RC is given there, will it make much difference for us? Because we are taking output at the emitter. Now, the only difference here is, if collector is directly connected to VCC, we could have directly written collector with the AC ground. Now, we cannot write it that way. We will have to write RC in parallel now. We will have to write, at the hybrid model, we will have to write RC also in parallel. Let us see. Now, Zi is Rs plus Rb parallel with HIC plus HFC into Re. The input impedance, we already have an expression for input impedance, plus there is this series resistance. So we have 300 plus Rb parallel with 1 kilo ohms plus 50 into 2.5 kilo ohms. But in this circuit, the value of Rb is not given. Let us simply proceed and let us see what we will arrive at. So now this is nothing but 300 plus Rb parallel with substituting all these values. HIC is given, HFC is given. So we can substitute those values. We will get around 300 plus Rb in parallel with 126 kilo ohms. Okay. Now it can be 300 plus 126 kilo ohms because Rb is larger. In general, always the base resistance for an emitter follower will be either 470 kilo ohms or 560 kilo ohms or sometimes 1 mega ohms, sometimes 2.2 mega ohms. In general, the emitter follower circuit is like that. So when Rb is much larger, when compared to this 126 kilo ohms, we can simply ignore the effect of the larger resistance. When a larger resistance and a smaller resistance are in parallel, the net resistance will be the smaller resistance slightly reduced. And if the larger resistance is much larger, its effect can be completely ignored. That way we can say the input impedance is 300 plus 126 kilo ohms, or approximately we can say 126 kilo ohms only. Because when compared to 126 kilo ohms, 300 ohms is negligible. Now this is Zi. Let us proceed with Z0. Here anyhow I have written it as 126.3 kilo ohms. 300 ohms is nothing but 0.3 kilo ohms. Let us proceed further for Z0. Z0, as we know, HIC by HFC parallel with Re, parallel with RL, because here we have RL now. So we are seeing impedance from this side, from the emitter side. We will ignore the effect of RC there, because there is this current source coming in between. As I had mentioned earlier, there is this current source coming in between, and even if RC is present and RC is connected to ground, we are going to measure the impedance from the emitter side, because we are taking output from the emitter. So we can completely ignore their proportion. So now Z0 is HIC by HFC parallel with Re, whole thing parallel with RL, because load resistance is given. So now substituting the values, we get 1K by 50 parallel to 2.5K, whole thing parallel to 4.7K. We get around 19.76 ohms, or we can say approximately 20 ohms. We always know that in case of an emitter follower, input impedance is very high, output impedance is very low. That is evident here. See, 126 kilo ohms is the input impedance, around 20 ohms is the output impedance. But voltage gain will be almost nearer to unity. Let us find it out. See, RE divided by HIC by HFC plus RE, we get 1K by 50, 1000 by 50 plus 2.5K. We get 2.5K divided by this value, we get around 0.992. That is very much nearer to unity. Okay. So, now current gain is AV into ZI divided by RE parallel with RL. At the output you have RE parallel with RL. At the input you have ZI. I had discussed about this earlier about how to find out the current gain. Voltage by current is nothing but resistance. That resistance part of output and input. So that way it is ZI into divided by RE parallel with RL. You can also write it as RE parallel with RL into AI equals AV into ZI. That also you can remember that way. That means current gain into output resistance equals voltage gain into input resistance. That way also you can remember the formula whenever you want to find out the current gain. Or you can simply write current gain equals voltage gain into ZI by Z0. That you can write. But this Z0 is now, in this case, it is RE parallel with RL. So, ZI by Z0 is the ratio from input to output. So, substituting all the values, we get around 76.8. So, we had a voltage gain unity, but we had a input impedance is 126 kilo ohms. We had a output impedance 20 ohms. And we had a load resistance here. By substituting all the values, we get around 77 times current gain. So, such exercises we had worked out in the first module also using the RE model for the emitter follower. Now we are doing the same thing for the emitter follower using the hybrid model. Results are similar, means emitter follower will give a current gain, it will give a high input impedance, it will give a low output impedance, but it will not provide a voltage gain. So, this emitter follower has high ZI, low Z0 and high AI. Lastly, I am coming to common base configuration. Let me quickly end this particular topic now, today itself. So, we already are familiar with the common base configuration of BJT. Okay, now base is connected to ground. So, at the input we have HIB. You will have to visualize emitter as input, collector as output. We have HIB and we have at the collector we have HFB into IE. B stands for common base. Then we have RC at the collector, we have RE at the emitter because base is grounded. Please recall the common base circuitry which we had discussed earlier. Now, ZI is directly RE in parallel with HIB. The similar expression we had in the RE model, where we had directly written ZI equals capital RE in parallel with small re. We had written that way. Z0 is RC itself because RC is in parallel with the current source. So, Z0 is RC itself. If at all we ignore that, HOB. If at all we ignore that, output admittance HOB. If at all we consider it, then it is RC parallel with 1 over HOB. Now, V0 is minus I0 into RC. What is I0 now? I0 is HFB into IE, V0 and HFB into IE. Parallel with RC is there, right? So, let us substitute for I0. I0 is minus HFB into IE into RC. That is the output current here. So, that minus HFB, what is IE now? VI by HIB into RC. Let us substitute for the emitter current in terms of the input. Input divided by HIB, that resistance at the input, that is this HIB. Total thing is VI here, and there is HIB here. VI by HIB into HFB is already there. So HFB into VI by HIB into RC. So V0 by VI, AV is V0 by VI equals minus HFB into RC divided by HIB. This way we get the expression for voltage gain. So with this, I am coming to the end of this particular topic of hybrid parameters and the usage of hybrid parameters in the AC analysis of the BJTs. Similarly, we can have hybrid parameters for JFET as well, but we are not going to discuss, and we do not have that in our syllabus as well, because already we had seen the RE model and we had seen such similar AC analysis, but in JFET we had used GM or transconductance for our purpose. If at all we have to use hybrid model for JFET, that is also possible that way, but again using GM. Anyhow, we are not going to discuss that in our syllabus itself. Okay. So I am ending today's class. From the next class onwards, we will start the low frequency analysis as well as the high frequency analysis of the BJT as well as the JFET circuits, and we will find out which capacitor is affecting our frequency response. So whatever I have discussed till now, you will have this much portion for the second internal test, and I will be posting the question bank in the Google class. I have already posted all the relevant material in the Google class. So study well, perform well, all the best for your test. Let me end today's class. If there are any questions, you can ask me. Otherwise, let me end today's class. Are there any questions?
But did you post the materials today?
Yesterday I have posted. In the Google class I have posted yesterday. I will be posting the question bank today. So for the first internal test, we had the complete first module, and in the second module, till JFET and BJT comparison, the basics of JFET, till then we had. So I had one PowerPoint called 2-1 for module 2. And I had the PDF given to you for complete module 1. Now, I have also posted 2-2, 2-3. Then I have posted the hybrid model. I have posted the module 3 PPT also. In the module 3 PPT, that until that chalk and talk is there now. Until then, all the basics about decibels we had discussed. Human auditory response, we had discussed all that. So you will have to study all those basics. Then the complete hybrid model we have discussed till now. This is there for the second internal test. In that PPT, which is named as 2-3, you can leave out the rest of the portion which is there after the slide chalk and talk, because that I have not yet discussed. I will be discussing that in the future classes. But until then, whatever you have discussed till now, right from the first internal test, you will have to study well. Anyhow, these modules have been easier according to my opinion, because if the first module is very much familiar with you, then automatically things will fall in place. If at all you have thoroughly understood the basics in the beginning of the first module, then all other things are going to fall in place. Okay, any questions? Fine then, if there are no questions, I will be ending today's class. I will be posting the attendance link in the Google class. All the best for your test. Perform well. See you in the next class.